So, generally the weaker versions of stationarity are defined by requiring that certain key statistical properties remain invariant with time, and we know by now that the some of the key statistical properties are mean, variance, but what we do not know is something called autocovariance. We have talked about mean, we have talked about covariance, that is because we were talking of general random variables, but now we are talking of random signals where we are looking at an ordered collection of random variables, and it is important for us to look at these jointly, and that is where the autocovariance notion comes into picture and leads us to this notion of weak stationarity. So, this weak stationarity has different names, it is called wide sense stationarity or second order stationarity. As you see from the definition why it is called second order stationarity. This order here is not in terms of distribution, it is in terms of moments, we are looking at second order moments. So, there are 3 requirements for a process to be called as weakly stationary or wide sense stationary or second order stationary. The first requirement is that the mean be independent of time. So, in the example that we just discussed, we had mu k as minus 2a by pi omega, correct, sin omega k, correct, good. Is this weakly stationary? It is not, it does not satisfy the first condition, which is a mean to be independent of time. On the other hand, so this was the case when phi was uniformly distributed between 0 and pi. If on the other hand, I have to remember my TA's advice, hold on. So, if on the other hand phi for the same problem, phi was uniformly distributed in minus pi to pi, we have already calculated the mean, haven't we? What is the expectation? 0, right. So, expectation of xk is 0, at least it satisfies the first condition. It does not mean it is weakly stationary, there are 2 other requirements that it has to satisfy, correct. Then the second requirement is that the process to have finite variance. So, obviously we are excluding a class of processes that can have infinite variance. Are there real life processes that do not satisfy the second requirement? Yes, there are many processes that have so called Cauchy distribution, like an earthquake process for example has infinite variance. I mean it does not really fall into this realm of weakly stationary processes, but we will not worry about that. We will fortunately we have a large class of processes that still satisfy the second requirement. You must appreciate that these 2 requirements are not as stringent as the requirements of strict stationarity, correct. The strict stationarity or even the nth order stationarity in distribution requires that the distributions remain invariant, but here we are only saying let the averages and the variances remain invariant with time and let them be finite, okay. Of course, in the first we have implicitly also meant that the mean should be bounded as well. I have not stated that, but you can note that down, mean should also be finite. If the mean is infinite, what happens? Is the second condition satisfied? Not. So, it is kind of understood. So, then the third requirement where now for the first time we come across this notion of autocovariance function, right. If you look at this definition, we will go over this definition in much greater detail a bit later, but upfront in order to give a complete definition of weak stationarity, I am introducing the definition of autocovariance here itself, it is like a curtain raiser, but we will look at this in detail later on. So, what is this autocovariance? Why is it called autocovariance? Because you are looking, first of all it is a covariance, then as the name suggests autocovariance function is a covariance, and now you understand why we studied covariance in great detail, correct. It is a covariance between any 2 observations that I randomly choose, located at instants k1 and k2, all right. And this autocovariance in general for any process can be a function of where these xk1 and xk2 are located, where these two observations are located, and that is why we have written the covariance as a function of k1 and k2, and a subscript, there is a double subscript indicating that you are looking at observations from within the same signal, which means there is a possibility of looking at covariance, computing covariance between two observations from two different random processes. That is where we run into cross covariance function, but we will discuss that later on. So, the notation has to be carefully understood. So, the third requirement is this autocovariance function be only a function of the time difference, pretty much like what we demanded for the nth order or the second order stationarity in distribution. Why do you think this is necessary? Why are we demanding that this autocovariance function be only a function of the time difference and not k1 and k2? Any explanation? You can think about it, it is fairly easy, the same kind of arguments that we used for requiring stationarity.
So, we are defining relationship between observations at two different time instances.
Right.
And they are saying that relationship should stay constant as we move in time.
What kind of relationship?
Linear relationship.
Very good. So, why is it that required? Why is that required? Practicality. It is sheer practicality, right. I mean, I collect a bunch of observations, that is one data record, and I am going to examine the dependency. Ultimately, what am I going to do? I am going to use this model for forecasting. So, if my statistical measures are telling me there is a dependency of the past, the present with two samples in the past, let us say, then I would like that to remain invariant, that dependency to remain invariant with time. What happens if it is not? That model that I have identified is only for that combination of observations. I can't use that model in future. So, each time we are going through the same argument, ultimately we want to make sure that the model that I build, that the analysis the inferences that I draw from the analysis of a single record hold good for future and probably for the past as well, right, definitely. So, here we have restricted ourselves to linear relationships straight away, because we know covariance is a measure of linear dependence. Straight away it gives you a feel that this definition is sufficient as long as you are in the linear world, or this definition, this relaxation of strict stationarity is good, is fine and is sufficient when you are developing linear models, all right. So, the wide sense stationarity therefore has three requirements: mean should be independent of time, variance should be bounded, and autocovariance should only be a function of the so called lag. What is the lag? The time difference. This also means that if I am looking, for example, at covariance between, let us say now x1, let me say here 1 comma 3, if it is wide sense stationary or weakly stationary, this should be equal to sigma 2 comma 4, and this can also be equal to sigma minus 1 comma 1 and so on. Any two observations that are spaced L samples apart should have the same linear dependence. What is this L? K2 minus K1, and that is what we call as the lag. So, this autocovariance function is not a mysterious one, it is after all at its heart a covariance measure, that is all. It is auto because the signal, you are looking at the same signal. It becomes cross when you do not climb that auto, you actually get into two different, you are analyzing two different series, correct. Any questions? Okay. So, these are the three requirements for a process to be called Whiteson stationary or weakly stationary, and also second order stationarity. Why do we call this a second order stationary? Because the covariance is a second order moment of the joint PDF, correct. So, under what conditions is this weak stationarity assumption justified? When we are living in the linear world. How do we justify this? Of course, we have already seen covariance is a linear measure, and we know that correlation is one. Of course, we have talked only about covariance. Very soon we will talk about autocorrelation, which is nothing but a standardized measure. We have seen the relationship between linear regression and correlation. They are synonymous to each other. So, intuitively it is very straightforward to see that this Whiteson stationarity is justified in the linear world. But let us understand this with a simple example. So, suppose I have a stationary process, okay, some station I am given it is stationary, and I am going to build a predictor of the form that I have given. That is, I am going to predict the random process at k using a linear function of two immediate observations in the past. And let us say the coefficients are minus d1 and minus d2. There is a reason why I have used minus d1, you can use d1 as well, does not matter. Now, what I want from you is the answers to the optimal estimates of d1 and d2. I am predicting a stationary process using this linear predictor, and I would like you to give me the optimal estimates. Optimal in what sense? That minimizes the mean square prediction error. We have already seen that. In other words, you have to tell me what are d1 star and d2 star that minimize expectation of xk minus x hat of k square. And the answers could be given in terms of the statistical properties. You will realize the purpose of this exercise once you get the answers, and it is kind of a corroboration of what we have answered at the top. Assume x to be 0 mean for convenience. Remember that since there are two unknowns, you will have to come up with two equations, right? At least two equations, and it is even sufficient if you tell me those two equations. A hint is that you will have to use the definition of autocovariance that we had introduced earlier, right. So, that when you are looking at expectations of products of two different observations, you will write them in terms of autocovariances. You have those equations with you? Sure. Or I can even write on the board for you. Sigma xx at any lag L is expectation of xk minus mu k, xk minus L minus mu k minus L. Since I am given it is stationary, we can actually assume that mu is the same and that the autocovariance is only a function of the lag L. I am given that it is stationary, it is very important. And you are additionally given that mu is 0. So, for this example, sigma xx at L is nothing but expectation of xk times xk minus L. Any answers from here or the other hall? Let me ask you, let me write here a matrix. Remember, we have two equations and two unknowns. So, two unknowns are d1 and d2. Ultimately, you should be able to write your equations in this form, as a set of two equations in a matrix form, and then eventually it boils down to a linear algebra problem. So, you will have to tell me what are the entries of this matrix and this vector here. if you proceed in a stepwise fashion, then you will not get lost. First expand this quadratic and then apply the expectations and rewrite your objective function in terms of the parameters and the autocovariances, and then differentiate the objective function with respect to the parameters d1 and d2. Any answers? The expectation of x square k would be the variance itself. Any answer from the other hall? Yes. Sorry? Here? Sigma, okay, let's drop the subscripts so that's easy. Okay, sigma here, okay, sigma of 1, all right, minus sigma 1, all right, and then okay, so let's see if there is, at least we need one more person to confirm this answer. What is sigma naught square? Hold on. So, that's probably got to do with the confusion with the notation. Sigma xx at 0, since I have not written the subscript, perhaps there is a confusion. Sigma xx of 0 is nothing but sigma square. So, either you specify the lag or you drop the lag and then you write it as a sigma square. So, that is the convention. So, this confusion will prevail for 1 or 2 lectures, and after that you will be comfortable. So, either you use sigma square or sigma at lag 0. Clear? Any other person with the same answer? Is it correct? It's fine. Very good. So, others of course can verify. You can always discuss with me after the class, but this set of equations are correct. So, you see we have actually moved from the world of random processes to the world of linear algebra, and that is always going to be the case. Now, we will, as you will learn throughout the course, keep visiting these kinds of equations for model building. What you see straight away is the optimal estimates. So, if you call them as d1 star and d2 star, the optimal estimates are actually only dependent on the second order moments. So, it is, if I want my model to remain invariant with time, or let me put it this way, if the autocovariances are invariant with time, then the model parameters are going to be invariant with time, which means that the model that I estimate from a finite record of data is potentially useful for future as well. That means some kind of stationarity is obeyed. So, this hopefully drives home the point that we made earlier, that the weak stationarity or Whiteson stationarity is good as long as we are in the linear world. The moment we move to the nonlinear regime, then other moments come in, that is higher order moments come in. What kind of higher order moments set in depends on the nature of the nonlinearity. We are not in a position to comment on that, because as I said, it depends on the nature of the non-stationarity and non-linearities as well. So, the point to remember is it is sufficient to assume a process to be weakly stationary as long as I am working with linear models. By the way, the bunch of equations that you see here were conceived by 2 different people, Euler and Walker, and these equations that you have are named after them somewhere in mid 1920s. These are called Euler-Walker equations. And they are very frequently used to estimate what are known as autoregressive models. In fact, the predictor that you see here in this example comes out from what is known as an autoregressive model of order 2, but we will discuss that in detail later on. Okay, so right now the purpose of this example was to show that it is sufficient to have invariance of second order moments up to second order moments as long as we are working with linear models. Good. Now again, like we saw in the case of prediction, we said a linear predictor is in general a suboptimal predictor compared to the conditional expectation, but they are identical when x and y are jointly Gaussian distributed. Likewise here, a wide sense stationary process or a weakly stationary process is also strictly stationary if the observations or if the random process itself is so called Gaussian process. What is a Gaussian process? The joint distribution of any set of observations that you pick have a joint Gaussian distribution. It does not matter how many you pick. You pick 2, then they should have a joint Gaussian. You pick 3 observations, jointly they should have a joint Gaussian, and so on, which means every observation should fall out of a Gaussian distribution as well. Why is this so? That is, why is a wide a Gaussian process which is weakly stationary a strictly stationary process as well? Because the Gaussian distribution is completely specified by the mean and covariance, and the wide sense stationarity demands that the mean and covariance remain invariant with time, and that means the distribution itself will remain invariant with time. Therefore, you have the result. Okay. So, Gaussianity has a lot of nice properties, and that is why that is the de facto assumption, default assumption that people make if they have to complete their degrees. Okay. And if you do not want to get into complications. All right. So, very quickly let us talk about non-stationarities, and we will continue our discussion tomorrow. So, we have talked about strict stationarity, we have talked about order stationarity in distribution, and we have also talked about second order stationarity in moments. So, it definitely it is worth, and there is a merit to discussing the different, at least some of the most popular types of non-stationarities that one encounters. It is impossible to discuss all types of non-stationarities. Generally speaking, that is broadly speaking, you can classify the non-stationarities into 2 types: deterministic type of non-stationarities and stochastic type of non-stationarities. In the deterministic category, you would run into non-stationarities such as polynomial trends, like we saw for the airline passenger data. There was a linear trend. It could be quadratic also, we did not test, but definitely there was a trend. What does it mean? The stochastic signal is riding on a horse that is a deterministic function of time. It is a polynomial function of time, or it could be any other deterministic function of time. It could be, for example, maybe a sine wave as well, but then those are special cases. You could also that is what we call as periodic. You could also have variance non-stationarities, and variances being deterministic functions of time. It need not be just the signal being signal having a trend. On the other hand, in the stochastic type of non-stationarities, the trends that we spoke of just now could be a function of a stochastic function, or could be the outcome of a stochastic process that is leading to the non-stationarity. And we shall discuss only one class of this stochastic type of non-stationarities, known as a random walk processes or the integrating processes. There are of course many more types of stochastic processes, but a large class of the stochastic processes that we encounter, particularly in econometrics and even in engineering, can be modeled as random walk processes. And we will also see that this random walk model can handle to a certain extent the deterministic trend type of non-stationarity. So, to give you a very quick example of a trend type non-stationarity, and now I have come back to the deterministic type of non-stationarities. For example, you could have x, which is your random signal, as a superimposition or superposition of 2 signals. One is a deterministic function of time and the other is a stochastic process. So, mu k is the polynomial function of time. If mu k is a linear function, then we say it is a linear trend. Let me give you an example. The airline passenger data that you see here on the top, we have also looked at this yesterday. If you see, there is a trend, correct, and on the face of it, it appears it is a linear trend. So, you can probably say it is a linear trend type non-stationarity. but one has to only confirm by fitting trends and seeing if a linear trend is able to explain the trend or a quadratic is necessary. What I have done is I have fit a linear trend and now I am showing you the residual, whatever is left over after fitting the trend. What do you see? Is it still stationary? It is not, because the variance is changing with time. At least if we have handled the mean non-stationarity, that we have captured, but the variance non-stationarity remains, and this is typical of any growth process. That has to be handled, and there are two different approaches to handle that. Either you can then perform a transformation to convert this non-stationarity process to a stationary signal, or you can fit what are known as Garch models, generalized autoregressive conditional heteroscedastic models. It's too much, but I mean, if you don't know anything, you can use it to scold someone, but that's what we used to do with terms in biology like protozoa and so on when we were in school. I had very great difficulty understanding, having a feel for platyhelminthes and so on, but now probably I'll appreciate it better. Anyway, so we will not talk of Garch models in this course. I am just saying that there are different approaches to handling non-stationary processes. We will continue our discussion tomorrow, where we will conclude with ergodicity and then go into autocovariance. Thank you.